You're not buying toys, you're building a capability portfolio. Every time you choose a STEM toy for your kid, you're placing a bet on which skills will matter in 2035, 2040, and beyond. The right kits teach soldering, algorithmic thinking, energy conversion, and systems design. The wrong ones gather dust after one weekend. My name is Chloe Miller, and I'm going to show you how to distinguish between both. You're listening to the STEM Lab podcast. Quick note before we dive in. Everything you're about to hear is researched, written, and verified by real human authors, but the voice you're hearing right now is AI generated. Just wanted to be upfront about that. If you're a regular listener, thank you. Seriously, it means a lot that you keep coming back. And if you're new here, welcome. You picked a good episode to start with. We drop new episodes every Monday, Wednesday, and Friday, covering everything from coding robots to renewable energy kits to building out a STEM workspace at home. Now, here's what we've got for you today. So what exactly are children's STEM toys? They're structured learning tools that teach science, technology, engineering, and mathematics through hands-on experimentation. Unlike passive entertainment, these products develop measurable technical competencies, circuitry knowledge, programming logic, mechanical advantage principles, renewable energy conversion, and spatial reasoning. They bridge the gap between theoretical classroom instruction and industry standard practice. A quality STEM kit doesn't simplify engineering, it scaffolds it. Take something like the Snap Circuits Junior SC100 Electronics Exploration Kit. Check the link below to see the current price. It teaches series and parallel circuits using the same principles you'll find in professional schematics. Or look at the LEGO Mindstorms Robot Inventor Building Set, link below for pricing. It uses motor encoders, gyroscopic sensors, and Python programming. That's the same toolchain robotics engineers use in prototype labs. But here's the truth. Most products marketed as STEM toys teach nothing transferable. They're batteries and light spectacles with proprietary apps that dead-end after 20 minutes of guided play. Real children's STEM toys offer progressive complexity, technical transparency, and open-ended application. You should be able to see how the mechanism works, modify it, and expand it as skills develop. If a kit hides its operation behind opaque plastic and a one-trick app, it's edutainment, not education. The defining characteristic? Concrete skill milestones. A 5-year-old working with something like the Learning Resources Botley 2.0 coding robot, link below, isn't just playing with a robot. They're mastering sequential instruction logic, a prerequisite for every programming language they'll encounter later. That's the difference. Now let's talk about how children's STEM toys actually work, the mechanism and learning architecture. Effective STEM toys operate on a layered learning model: tactile manipulation at the foundation, conceptual pattern recognition in the middle, and generalized problem solving at the top. You can't skip layers. A child who hasn't internalized cause and effect through physical experimentation can't abstract those relationships into code. Start with the physical feedback loop. Begin with manipulatives: gears, levers, circuits, motors. These deliver instant, visible feedback. Push a button, the LED lights. Flip the gear orientation, the mechanism reverses. I've watched dozens of kids discover Ohm's law, not through a formula, but by adding resistors to a circuit and watching the LED dim. That visceral experience anchors the abstract concept later. The Learning Resources Gears set for ages 3 to 5 teaches mechanical advantage, rotational direction, and gear ratios through chunky, interlocking plastic pieces. You'll see your child experiment with different configurations to make the whole system spin. That's applied engineering, even if they can't name it yet. No batteries, no screens, no hidden logic. Moving to the next layer, screen-free coding. Products like the Botley robot use physical command tiles that represent programming functions: forward, turn left, loop. Children sequence these tiles, press go, and watch the robot execute. They're learning function order, debugging when the path doesn't match expectations, and iterative refinement, all without staring at a screen. This stage is critical. Kids who jump straight to screen-based block coding often struggle with spatial reasoning and manual dexterity integration. The physical tiles force them to plan the entire sequence before execution. It's slower, more deliberate, and far more durable as a cognitive skill. By ages 8 to 10, children are ready for industry-standard platforms. The Arduino Starter Kit, link below for current pricing, is the gold standard here. It's the same microcontroller used in university engineering programs, open-source hardware projects, and commercial prototyping. Kids learn C++ syntax, digital input-output control, sensor integration, and circuit design. Projects scale from blinking an LED to building a weather station with temperature, humidity, and barometric pressure sensors. The Arduino ecosystem is infinitely expandable. Once your child outgrows the starter projects, they can add servo motors, OLED displays, RFID readers, GPS modules, any component with a library. This isn't a toy with a shelf life. It's an entry point into maker culture and professional embedded systems development. Lab specs matter here. Most Arduino boards run on 5-volt USB or 7 to 12-volt barrel jack input. Safe, low voltage, but you'll need a clean workspace away from liquids. For connectivity, it's USB to computer for programming. Some advanced boards add Wi-Fi or Bluetooth for Internet of Things projects. As for expandability, there are thousands of shields, sensors, and modules available. Just check pin compatibility before purchasing add-ons. And durability? Circuit boards are fragile. Invest in a case and silicone jumper wires. They're more durable and solid core for repeated use. Here's where things get really interesting: the renewable energy bridge. Solar and wind energy kits teach energy conversion, storage, and load calculation. These are skills directly applicable to climate solutions work. The THEMS and Cosmos Wind Power 2.0 kit, link below, includes a working turbine, gearbox configurations, and DC motors that function in reverse as generators. Kids measure voltage output at different wind speeds. You can use a box fan. Calculate efficiency losses through the drivetrain, and experiment with blade pitch angles. These aren't hypothetical exercises. When your 12-year-old calculates that their 3-watt solar panel needs 6 hours of direct sunlight to fully charge a 3,000 milliamp hour battery bank, they're doing the exact math I use sizing off-grid systems for my own workshop. Take something like the OWI robotic arm Edge with USB PC interface, link below. It can run on solar power. Connect it to a panel kit and watch your child troubleshoot power management when the robot stalls on cloudy days. That's real-world problem solving, not simulation. So why do children's STEM toys matter? It's about skill investment for an uncertain future. The jobs your child will work don't exist yet, but the foundational competencies do. Systems thinking, iterative prototyping, cross-disciplinary integration, and technical literacy. Children's STEM toys aren't about memorizing facts. They're about building cognitive infrastructure for adaptive problem solving. Consider algorithmic thinking. Every software engineer, data analyst, and automation specialist relies on the ability to decompose complex problems into sequential steps, identify patterns, and optimize for efficiency. That's exactly what happens when a 7-year-old programs a robot to navigate a maze using a screen-free coding kit. They're not just learning to code, they're learning how to think algorithmically, a skill that transfers to any domain. Or take renewable energy kits. Climate change will define their generation. Kids who understand photovoltaic efficiency, energy density, and conversion losses today will design the distributed solar grids, community wind cooperatives, and regenerative agriculture systems of 2040. The THEMS and Cosmos Solar Power 2.0 kit teaches watts, voltage, current, and battery chemistry through 15 buildable models, from a solar car to a charging station. Your 10-year-old who measures panel angle versus output is learning the same optimization calculations I use on my own rooftop array. The ecological urgency is real. We don't have time for a generation that treats technology as magic. They need to see inside the systems, understand energy costs, recognize greenwashing, and build solutions themselves. That starts with a soldering iron, a multimeter, and a kit that doesn't hide its guts behind injection-molded plastic. And here's the practical side. STEM fluency is economic resilience. Automation will displace millions of routine jobs. The skills that remain valuable, creative problem solving, technical troubleshooting, system design, are exactly what quality children's STEM toys cultivate. You're not preparing them for a career, you're preparing them to invent careers. Let's break down the types and variations. Not all children's STEM toys serve the same developmental function. Effective learning paths combine multiple categories in a progression that builds complexity over time. First, mechanical and construction systems for ages 3 to 8. These build foundation skills, spatial reasoning, mechanical advantage, structural stability. Products like Lego Technic, Connects, Engino, and Marble Runs. These teach gear ratios, lever classes, and load distribution through tactile experimentation. No power source required, pure physics. Second, screen-free coding and logic games for ages 4 to 9. Algorithmic thinking without screen time. The Think Fun Gravity Maze Marble Run brain game, link below, uses spatial logic and sequential planning. Same cognitive load as programming, zero device dependency. For robots, the Botley and Cubetto, now discontinued but still available secondhand, use physical programming tiles, develops function sequencing, debugging, and loop logic. Third, electronics and circuitry kits for ages 8 to 12 and up. Real components, real schematics. Snap circuits, Little Bits, and Elenco teach series and parallel circuits, resistor function, transistor switching, and sensor integration. Milestone, soldering your first circuit. That's a permanent skill. I still use the soldering technique I learned at age 11. Fourth, robotics platforms for ages 8 to 14 and up. Industry standard programming and mechanical integration. Lego Mindstorms, Vex IQ, MakeBlock MBot, and Arduino-based robots. These combine motors, sensors, and code. Skills include motor control, sensor feedback loops, IPD algorithms, and multi-threaded programming. Fifth, renewable energy and environmental systems for ages 9 to 14 and up. Solar, wind, hydroelectric, and fuel cell kits. Teaches energy conversion efficiency, storage systems, and load calculation. The Horizon Fuel Cell Car and Refueling Station Kit, link below, demonstrates electrolysis, hydrogen storage, and fuel cell operation, technology critical for grid-scale renewable storage. Bonus, these projects have measurable real-world impact. Your child's solar oven can actually cook food. Their wind turbine can charge their own devices. And sixth, 3D design and additive manufacturing for ages 10 and up. CAD software like Tinkercad or Fusion 360, plus a beginner 3D printer like the Creality Ender 3 V3 SE, link below for pricing. Skills, parametric design, material properties, iterative prototyping. This is how modern engineers work. Design digitally, test physically, refine. Each category prepares for the next. You can't skip mechanical foundations and jump straight to robotics. The child won't understand torque, friction, or structural design, but layer them correctly, and by age 12, your kid can design a 3D printed, solar-powered robot that navigates autonomously. I've seen it dozens of times. Before you buy a single kit, you need to think about lab specs, infrastructure, compatibility, and durability requirements. Children's STEM toys aren't plug and play. They need space, power, storage, and for advanced projects, ventilation. Power and connectivity first. Most robotics kits, circuit boards, and electronics projects run on batteries or USB power that's 3 to 12 volts, safe for unsupervised use. But 3D printers, soldering irons, and some motor-heavy robotics platforms require AC power from wall outlets. Install GFCI outlets in your workspace. Computer dependency is another factor. Arduino, Lego Mindstorms, and Vex platforms require USB connection to a PC or tablet for programming. Check operating system compatibility. Many kits dropped Windows 7 support in 2024. And when it comes to cloud versus offline, some kits like Sphero and Wonder Workshop require cloud-connected apps. I avoid these. Internet outages shouldn't halt learning. Prioritize kits with offline software. Storage and organization matter more than you'd think. Circuit components, sensors, motors, and fasteners multiply fast. Invest in a compartmentalized storage system. I use Plano tackle boxes because they're cheap, durable, and stackable. Label everything. Loose jumper wires are chaos. Expandability and ecosystem lock-in. This is critical. Avoid proprietary ecosystems. If a kit uses custom connectors, non-standard voltage, or app-exclusive programming, you're locked into that manufacturer's upgrade path. The moment they discontinue the product line, and they will, your investment is obsolete. Prioritize open-source platforms. Arduino is a universal microcontroller with thousands of compatible components and an active community. Raspberry Pi is a Linux-based single-board computer that runs Python, Scratch, and full desktop applications. Vex and Tetrix are metal-based robotics platforms with standardized mounting patterns compatible across product generations. Durability for repeated use is non-negotiable. Cheap plastic gears strip, thin PCB traces crack, flimsy servo motors burn out. I test durability by disassembling kits and inspecting component quality. Red flags include injection-molded gears without metal inserts, ribbon cables instead of individual wires, and adhesive-mounted electronics, impossible to repair. Durable choices. Lego Technic and Mindstorms use ABS plastic that lasts decades. I still have functional pieces from my childhood. Vex IQ and EDR use aluminum extrusion frames, steel shafts, metal gears, built for competition-level abuse. Arduino boards with through-hole components are repairable. Surface mount boards are not. Avoid cheap clones. Watch out for consumables and subscription traps. Avoid subscription-dependent kits. Some manufacturers lock programming features, lesson plans, or even basic functionality behind monthly fees. The Wonder Workshop Dash robot is a solid robot, but advanced programming requires their paid Blockly app. Hard pass. Monitor consumable costs too. 3D printing filament runs around $20 to $25 per kilogram of PLA. A beginner uses about 2 to 3 kilograms a year. Batteries. Rechargeable AA and AAA batteries like Eneloop pay for themselves after a dozen cycles. Single-use alkalines are wasteful and expensive. Replacement components like servo motors, sensors, and motor drivers will eventually fail. Check that replacements are available and affordable. Now, let's tackle some frequently asked questions. What age should children start with STEM toys? Children can begin foundational STEM skills as early as age 3 with mechanical construction toys like wooden blocks, simple marble runs, and gear sets that teach cause and effect and spatial reasoning. Screen-free coding robots work well from ages 4 to 5, building sequential logic without device dependency. Electronics kits with soldering and circuit design typically start around age 8, while industry-standard platforms like Arduino and robotics competitions suit ages 10 and up. The key is matching tools to manual dexterity, abstract reasoning ability, and sustained attention span, not arbitrary age brackets. Focus on skill readiness over chronological age and structure a progressive path that layers complexity gradually. Do children's STEM toys require expensive computers or tablets? Many foundational STEM toys require no screens at all. Mechanical construction sets, circuit boards with physical components, screen-free coding robots, and renewable energy kits all develop critical skills without digital devices. When programming is required, Arduino, Lego Mindstorms, Vex platforms, any computer from the last 5 years running Windows 10 or 11, macOS 10.15 or later, or Ubuntu 20.04 or later will work fine. Budget Chromebooks handle block-based programming like Scratch and Blockly, though they struggle with Arduino IDE and advanced CAD software. For 3D design work like Tinkercad or Fusion 360, you'll want at least 8 gigabytes of RAM and a dedicated graphics card. iPads work for some robotics apps, but I avoid iOS-exclusive ecosystems. They limit expandability and long-term flexibility. Prioritize offline-capable software and cross-platform compatibility to avoid expensive upgrade cycles. How do I know if a STEM toy teaches real skills or just entertains? Real STEM toys reveal their mechanisms, scale and complexity, and connect to industry-standard tools or principles. Ask 3 questions. Can you see how it works? Transparent cases, exposed gears, readable schematics beat opaque plastic shells. Can you modify or expand it? Open source platforms, standardized connectors, and compatible ecosystems enable growth. Proprietary systems dead end. Does it prepare for professional tools? Arduino leads to embedded systems programming. Lego Windstorms uses Python. Renewable energy kits teach the same physics I use on commercial solar installations. Entertainment products hide their operation, offer one predetermined outcome, and rely on spectacle over understanding. If the toy stops working when the batteries die or the app updates, it's edutainment. If your child can troubleshoot, repair, and repurpose it, it's education. Concrete skill milestones, like can solder a circuit, understands gear ratios, debugs sequential logic, those distinguish learning toys from toys. Are renewable energy STEM kits worth the investment compared to traditional electronics kits? Yes, especially for ages 9 and up. Renewable energy STEM kits teach the same circuitry, voltage, and current principles as traditional electronics kits, but add energy conversion efficiency, storage systems, and real-world optimization challenges that traditional kits omit. Solar panel experiments require calculating angle of incidence, shading losses, and battery charge rates, practical skills for grid-scale renewable installations. Wind turbine kits demonstrate mechanical to electrical energy conversion, gear ratio optimization, and load matching. These aren't abstract exercises. They're the exact problem sets engineers tackle in climate technology careers. Renewable energy kits also have measurable real-world output. Your child's solar panel can charge their phone. Their wind turbine can power an LED array. Their hydroelectric setup can run a small motor. That tangible impact builds intrinsic motivation far more effectively than lighting an LED for the 15th time. Pair them with traditional electronics education for comprehensive understanding. How do I transition my child from beginner STEM toys to advanced engineering platforms? Build a progressive learning path that layers tactile manipulation, symbolic representation, and abstract tool fluency. Start with mechanical systems for ages 3 to 8 to establish spatial reasoning and physics intuition. Move to screen-free coding for ages 5 to 9 to develop algorithmic thinking without device dependency. Then, introduce electronics kits for ages 8 to 11 for circuit theory and component function. Once your child can solder, read schematics, and debug hardware, transition to industry-standard platforms like Arduino for ages 10 and up for embedded systems programming, or Lego Mindstorms and Vex for integrated robotics. Layer renewable energy projects throughout to contextualize electricity concepts in real-world applications. The critical mistake is skipping foundational stages. Kids who jump straight to Arduino without prior electronics experience struggle with voltage and current relationships, component selection, and physical troubleshooting. Structure the path around capability milestones, not age ranges, and allow 12 to 18 months per stage for skills to solidify. Here's what it all comes down to. The children's STEM toys you choose today determine which problems your child can solve in 2040, not which job they'll get, which problems they can tackle. Climate adaptation, distributed manufacturing, regenerative agriculture, open source medicine, decentralized energy. These challenges require people who can prototype, iterate, and build outside institutional structures. That starts with a $30 Snap Circuits kit and progresses through Arduino, 3D printing, and solar panel optimization. It's not about early college prep or resume padding. It's about building the muscle memory of making things work when the instructions run out. Every kid who learns to solder can repair their own electronics instead of landfilling them. Every kid who programs a robot understands that algorithms aren't magic, they're debuggable logic, written by fallible humans. Every kid who measures solar panel efficiency internalizes that energy is finite, convertible, and worth optimizing. You're not preparing them for the future, you're giving them tools to build the future. Start with one kit, one concrete skill, one measurable milestone, then layer the next. That's how engineers are made. Thanks for listening to this episode of the STEM Lab podcast. We're back every Monday, Wednesday, and Friday with new episodes, so you've always got something to look forward to. If you found this helpful, I'd really appreciate it if you'd leave us a 5-star rating and a quick review. It makes a huge difference in helping other people discover the show when they're searching for STEM education resources. And if you haven't already, hit subscribe or follow so you get notified the moment a new episode drops. See you next time.